Welcome to this video lecture on the subject transmission lines and antennas. So in this lecture we are going to see about transverse electromagnetic waves. So generally the transverse waves are classified as TE, TM and TEM waves. These are transverse electric, transverse magnetic and TEM waves. So in the waveguides, normally in rectangular waveguides, TE and TM modes are allowed to pass. So and TEM waves are normally used in transmission lines. So these are the comparison between the three modes. So first one, transverse electric, where the electric field component along the wave propagation direction is 0. So Ez is 0 and the magnetic field component is available. So Hz not equal to 0. So the only magnetic field component is present along the direction of wave propagation. And the second case is the transverse magnetic, so in which the magnetic field along the direction of propagation is 0. So Hz equal to 0 and second component Ez not equal to 0. In transverse electromagnetic wave TEM mode, so both the components Ez and Hz are 0. So dominant mode or dominant wave. So for the TE fields, transverse electric fields, the components present in the wave during the electromagnetic wave propagation are Ey, which is given by the equation of C1 sin m pi by a into x e power minus j beta z, where this beta refers the phase shift constant, z is the direction of propagation, and other fields are Hx and Hz. Here we can note that Ez is not available because Ez is 0 in the transverse electric wave, and the dominant mode is the lowest cutoff frequency available for this lowest cutoff frequency for the TE mode. So TE M0 wave or mode can be written as, so for the all the fields will vanish when m equal to 0. So m equal to 1, the fields are present. So the lowest order mode is the TE10. So TEM waves, for TE wave lowest order mode is TE10 where m equal to 1. So because m equal to 0 makes all the fields vanish. So for TM wave, for m equal to 0, Ez equal to 0. So but there are other two fields Ex and then Hy. For TM wave we know Hz is always 0. So for TM wave we know Hz is always 0. So Ez and Hz equal to 0 for m equal to 0. So this component is known as the TEM mode. So it is entirely transverse. So this special case of wave or mode is known as the TEM wave or TEM mode or principal wave. So it is the familiar type of wave propagated along the ordinary two-conductor transmission line operating in low frequency. So it is a special case of TM wave. So for the TM wave fields are given by Ez, Hy and Ex, where Hz component is not available. So where gamma is the propagation constant, it can be substituted as J beta in this equation. And Hz equal to 0 for TEM waves and Ez is also 0. So the other components are Ex and Hy. It is given by beta C4 divided by omega epsilon. Here beta is the phase shift constant and omega is the angular frequency, epsilon is the permittivity. So Z is the direction of wave propagation. And characteristics of TEM waves are given by phase constant beta. So it is calculated by substituting m value equal to 0. So beta equal to square root of omega square mu epsilon. The second term becomes 0. So we get beta equal to omega square root of mu epsilon. So omega is the angular frequency, mu is permeability of the medium, epsilon is the permittivity. So beta varies linearly with frequency and therefore wave propagation takes place without dispersion. And next is the phase velocity. So it is given by the formula omega by beta. So we can substitute omega and then beta values. So omega is keep it as such and beta is substituted as square root of omega square mu epsilon. The second term m equal to 0. So the cancelling omega we get 1 by square root of mu epsilon. So for the free space condition, it is equivalent to c, that is it is equivalent to velocity of light. Next characteristic is guide wavelength. It is lambda g. So the wavelength is given by 2 pi by beta. So by substituting beta value and m equal to 0, we get 2 pi by square root of omega mu epsilon, where 2 pi by omega is given by the 1 by reciprocal of frequency. So it is c by f. So lambda we get c by f. For air dielectric, this equation can be used. This is an activity. And TEM wave characteristics, next component is cutoff frequency Fc. So Fc is given by m by 2a square root of mu epsilon. So for substituting m equal to 0, we get 0. Next, wave impedance ZTEM. So it is given by the ratio of electric field component Ex divided by Hy. So by substituting Ex and Hy, we get beta by square root of omega epsilon. So after substituting the beta value as omega square root of mu epsilon, we get square root of mu by epsilon, which is known as the intrinsic impedance. So for the free space, this value is equal to 120 pi ohms. So this is the intrinsic impedance of free space. And E and H fields, electric field and magnetic fields in XY plane are given. So magnetic field lines are given as arrow marks, and the electric field lines are given as Ex equal to beta C4 divided by omega epsilon r. And electric field and magnetic field components in the XZ plane are given. So magnetic field lines are given as downward. These are the assessment questions. So differentiate TEM wave from TE and TM waves. And what do you infer from the cutoff frequency of the TEM wave? And TEM wave is a special case of which wave for m equal to that value. So here the TEM mode is a special case of TM wave, and cutoff frequency of TM wave is 0. So this is the lowest cutoff frequency, and differentiate TEM wave from TE and TM waves is that. So TEM wave is the special case of TM when m equal to 0, and wave impedance of TEM wave is equal to intrinsic impedance of this free space. So these are the references. Thank you for listening this lecture.